Welcome back to another MECH 1000 video. We are continuing our discussion of thread specifications in our blueprint reading textbook. And we've mentioned up until now, and all the examples we've looked at have had unified national threads, unified national coarse, UNC or UNF for fine, or UNEF for extra fine. And so we're going to look a little more closely at exactly what a unified thread form means. It basically has to do with the actual shape of the threads. So if we were to look very closely at the threads, and these could be representing internal or external threads on a bolt or inside a hole, the pitch of a thread series is the distance between the threads. So essentially the size of one thread. And unified national threads have this angle. The sides of the threads make a 60-degree angle, and they have flattened tops. And this unified thread series was developed in 1948 and is essentially a compromise between two older threads that had been used earlier, the American National and British Whitworth threads. So this is sort of a compromise or combination of those two threads. And this is what we use primarily in the US, with the possible exception of metric threads. Because as manufacturing becomes more and more international, I think we are seeing more and more metric fasteners in a lot of the products we use. And according to our textbook, the unified thread series is interchangeable with American national threads that are same diameter and pitch. So I mentioned just a moment ago that the unified thread series has, or the unified national thread form has three different series: coarse, fine, and extra fine. And those are abbreviated UNC, UNF, and UNEF. So why would you want to have coarse threads? Well, coarse threads are easier to make, so they're cheaper, and because the threads are larger, for every one turn of the fastener, it advances it further. So it makes for quicker assembly or disassembly. Also, the larger threads are less affected by potential corrosion. So if you're going to be using a threaded fastener in a situation where it might get a little bit rusty, larger threads are going to be less likely to seize than finer threads. So fine threads, on the other hand, allows for better fine-tune adjustment because of the smaller threads. If you turn the fastener a full rotation, it doesn't advance as much, so it gives you a little bit more control over how far to advance that fastener. It's also useful when the depth of the hole that you are threading into is limited. So that's what it means when it says the length of engagement is smaller, and yeah, so when you are perhaps drilling into a cylinder or a pipe or something where you have a limited amount of thickness, those fine threads are going to be more desirable. Of course, it does then subject you to more potential seizing due to corrosion. So it's just a trade-off between the benefits of coarse, coarse being faster assembly, less affected by corrosion, cheaper to make. Fine threads are going to be a little bit more expensive to make. They're more susceptible to corrosion, but does allow for better fine-tuned adjustment and works better when you have a smaller length of engagement. And then extra fine, it's basically the same advantages and disadvantages of fine threads, but even more so. So when you want even finer adjustability, when you have even shorter lengths of engagement, or you're drilling into a very thin-walled tube, or something along those lines, it is more helpful to have extra fine threads. And that last little bit of alphanumeric information on the end of a typical hole specification, 1A or 2B, the number refers to the class of fit. So a class 1 is for loose fitting applications. So there's there could be a little bit more of a gap between the external and internal threads when they fit together. Class 2 is standard. That is essentially the default value. And Class 3 is where you need a very close fit between the threads, the external and internal threads. And if you don't see anything labeled at the end of the hole specification, you can assume that Class 2 is what is being used. And also, the A or B, which indicates internal or external threads, is oftentimes pretty obvious, and so is not always specifically mentioned in the hole specification. Now, as far as representing these threaded holes on our drawings, we can do it in a couple of ways. Two basic options here for showing the threads of the internal threads in a hole. There's this schematic method, which is not really hyper realistic, but sort of alludes to what the threads sort of look like. So it's slightly more realistic, showing representation of what those threads might look like inside the hole. But then there's also this simplified method, which is probably used more frequently, where we just use a dashed hidden line just outside the visible line itself. So it just sort of shows a bit of an outline around that hole, indicating the presence of threads. So this simplified method is obviously simpler to draw and doesn't quite provide the same sense of realism, but rather communicates to you almost more as a symbol that threads are present. And when the hole is seen from its end, as we look at it here, we see the dashed line surrounding the hole, again outlining it almost like a halo, and that dashed line indicates the presence of threads. One thing to look out for is when you see the hidden line surrounding the hole like this, that can be used to show the presence of threads, but it could potentially also be showing a chamfer on maybe the back side of the part. So a chamfer results in two concentric holes, and if that chamfered hole is on the back side, it would be shown with a hidden line. So what you need to do whenever you see a hole that is surrounded by a hidden line like this, you need to make sure that you then look at the corresponding notation and see, is this in fact a threaded hole? So the presence of something here like this, 0.312-18 UNC, that tells us that this is definitely a threaded hole because it is specifying the size of the threads and the thread series and the class of fit. Okay, let's look at an example exercise here. What type of section is shown? So we just talked about section views, I believe in the last chapter or maybe the chapter before. So this is just a little bit of a review. And the hint here in parentheses is telling us to observe the cutting plane line. So the cutting plane line comes across here and then angles down, it rotates down, and then comes up at an angle and over, and it jogs up and across. So anytime you have a cutting plane line that is not a straight line, it's kind of moving around in order to pass through intentionally the points of interest in the object, that is what we call an offset section. Okay, let's move on to some new material here. In this chapter, we're talking about threaded holes. How many threaded holes does this part contain? So we see here a hole that has a dashed line around it, but we need to make sure that's actually a threaded hole. And yeah, we can see UNF, Unified National Fine. So there's 1, there's 2, there's 3, 4, 5, 6, 7, and let's make sure that these are actually threaded. Yep, we can see UNC. So I count 7 threaded holes, and that's correct. What representation method is used to illustrate the threads in the top view? So in section views, the schematic format might be a little bit more common, and that's what we're seeing here. This way that it's illustrated with these lines that evoke the idea of threads. That's what we call the schematic method of representing those threads. Are the threads right hand or left hand? So as we look at the hole notes, if they were left-handed, we would see an LH. If we look at these, at this hole note, I don't see any LH there. I look down here, look at that hole note, I don't see an LH in that either. So if it doesn't specify, if there's no LH or RH, we just assume that they are in fact right-handed. How many full threads will each number 12 hole contain? So this is probably one of the more challenging types of questions. It's a common type of question that you'll see in an assignment with threaded holes. How many threads are there in each number 12 hole? So first of all, we have to find the number 12 hole. If we look down here, nope, doesn't look like that. That's a number 10 hole with a number 26 tap drill. Up here, there we go. There's our number 12 hole. So that's number 12 hole. We need to know the depth of this hole. Okay, so no depth is specified in the hole note, so therefore it must be a through hole, and it goes all the way through the part, which has a thickness of 1/2 inch. Now, like this dimension A is not given, but this whole object, this whole reservoir cover, is made out of stock material that has a thickness of 0.5 inches. So that's the thickness here, 0.500 inches. And so if the hole here is 28 threads per inch, TPI, and the depth of the hole is only 1/2 inch, that means there are 14 threads in that hole. All right, I think this will probably be a good stopping point. Looks like we're going to look at another example exercise to start off the next video.